A solar flare doesn't travel to Earth slowly. Its first punch arrives at light speed in 8 minutes. In the wrong place, at the wrong time, that is enough.
Most people imagine a solar storm as a distant spectacle. Auroras, pretty skies, maybe a few satellite glitches. But the fastest part is not the plasma cloud. It is the radiation hitting our upper atmosphere first. That impact can black out radio, degrade navigation, and confuse timing. Then the grid inherits the chaos through physics, not fear. In this tape, you will follow the failure chain, from the first flash to the first wrong decision, and why minutes is not exaggeration.
Picture a control room before dawn. Everything is quiet, and the load is steady. Airports run on schedules, and ships follow GPS routes. Emergency services rely on radio when networks fail. Now imagine the sun produces a sudden X-ray surge. No warning siren reaches your city first. The flare's energy reaches Earth in minutes. It strikes the day side of our planet immediately. High-frequency radio can drop out without drama. Aviation routes over oceans can lose reliable voice contact. Navigation signals can degrade as the ionosphere distorts. Nothing has exploded yet, but coordination is already slipping. This is where the threat hides. Modern infrastructure depends on invisible alignment. Precise time, stable frequency, clean signals, predictable demand. Space weather attacks those assumptions first, not by burning cities, but by blinding systems.
The first wave is called a radio blackout. Solar X-rays change the ionosphere's chemistry quickly. Radio waves that bounce off it can vanish. That is not a rumor. It is documented behavior. Next comes navigation trouble. GPS and other GNSS signals cross the ionosphere. During geomagnetic storms, electron density becomes turbulent. Position errors grow, sometimes far from the poles. For many people, that is an inconvenience. For synchronized systems, it is a warning shot. Now zoom out to the grid. Electric power is not one machine. It is a continent-sized agreement, maintained every second. Operators balance generation and demand in real time. Protection systems watch for abnormal currents and voltages. If they see danger, they trip lines to prevent damage. Geomagnetic storms add a new kind of current. Not AC, but slow quasi-DC currents from Earth itself. These geomagnetically induced currents push into transmission lines. They can drive transformers toward half-cycle saturation. When that happens, the grid starts behaving strangely. Reactive power demand rises. Harmonics spread through the network. Protection relays may misread what they see, and the operator's screen fills with alarms. This is where minutes becomes real. A flare can cause immediate communication loss on the day side. The storm can begin stressing the grid quickly afterward. Even conservative planning documents assume fast electrical effects. Some impacts are treated as effectively instantaneous, within seconds. Thermal damage takes longer, but instability does not. So the danger is not one giant switch. It is a cascade of small breaks in coordination. A crew cannot call a pilot on HF radio. A backup route depends on GNSS timing that drifts. A grid operator loses clean telemetry from remote substations. Then one line trips and load shifts elsewhere. The system compensates until it cannot.
The flare hits. HF radio drops across the sunlit hemisphere. Controllers switch frequencies, but the noise persists. Some links recover, then fail again. On the grid, the storm intensifies. Currents enter long transmission corridors like ghost power. A transformer core saturates for part of each cycle. It pulls reactive power harder than expected. Voltage sags and alarms multiply. One protective relay trips a line. Power reroutes through a parallel corridor. That corridor now carries more current and more stress. Another relay trips, trying to save equipment. The grid fractures into islands of power and demand. Frequency wobbles. Generators fight to stay synchronized. Some disconnect automatically to protect their turbines. Load shedding begins, intentionally at first, then it becomes uncontrolled and wide. City blocks go dark. Traffic lights fail in waves, not all at once. Cell towers stay up briefly on batteries, but backhaul links weaken as routing collapses. Hospitals switch to generators, and fuel becomes a clock. Nothing about this looks like a movie. It looks like normal systems making safe choices. Each choice is rational in isolation. Together, they can produce a blackout. Hours later, the aurora finally becomes visible. People film the sky while the ground stays uncertain. The damage is not just darkness, it is disruption, lost coordination, and delayed recovery. A severe storm can stress transformers and equipment. Some heating effects build over minutes, not seconds. Even without permanent damage, restoration is slow. Crews must re-energize lines in a safe sequence. They must confirm stability before reconnecting islands. And they must do it while communications remain degraded. This is why space weather is a civil risk. NASA and NOAA describe real impacts on technology: radio blackouts, navigation disruption, and power problems. Science you can hear, dread you can feel. So ask yourself one simple question: if the sun blinked at us tomorrow, would we notice fast enough?
This is not a prophecy. It is a system story, written in physics. We monitor the sun and we issue alerts, but prediction is hard and timing is unforgiving. If you want the next tape, subscribe. The archive keeps growing. And if you ever see the aurora farther south, remember this: the sky is not only beautiful, sometimes it is a warning.